In this lecture, I will discuss about the wave function and its meaning. And this lecture is from the textbook Quantum Mechanics by March Bezer. So, what is wave function? As we have seen, facing us at the outset is the fact that matter, such as electron, exhibits both particle nature as well as the wave nature. This duality was described in deliberately vague language by saying that the de Broglie relation associates a wavelength with a particle momentum. Now, why there is vagueness? The vagueness reflects the fact that particle and wave aspects, when they show up in the same thing, such as the electron, are incompatible with each other unless traditional concepts of classical physics are modified to a certain extent. Now here, what is traditional concept? Here traditional concept means that we have to define the position of the object specifically. For example, when in classical physics we define the position of a particle with respect to a particular three-dimensional coordinate system. So what we have to do? We have to specify the position. Wave means a pattern spread out in space and time, and it is characteristic of a wave that it does not define a location or position sharply. So there is some contradiction between the wave aspect and particle aspect, because lambda is equal to h by p. Here lambda comes from the wave aspect and momentum comes from the particle aspect. But simultaneously, specification of the position and momentum is very difficult, because if you consider the wave aspect, then you cannot define the location of the position sharply. But here lambda is related to the momentum p. So according to classical physics, if you tell about the momentum, then what you have to do? You have to specify the position correctly. Historically, the need for a reconciliation of the two seemingly contradictory concepts of the wave and particle was first addressed by Niels Bohr. And there is a principle, the name of the principle is Bohr's complementary principle. Now, what are complementary variables such as position and momentum, energy and time? These are the complementary variables, and you cannot measure simultaneously those complementary variables. So, this problem was first addressed by Niels Bohr. Now, the quantum theory basically give an account of the discreteness of certain physical properties. For example, discreteness of the energy levels in an atom or a nucleus. However, this discreteness did not first enter physics with the Bohr atom. Even in classical macroscopic physics, discrete or quantized physical quantities appear naturally as the frequencies of vibrating bodies of finite extension, such as strings, membranes, or air columns. And we speak typically of the normal modes or natural modes of such systems. So these modes are actually discrete or quantized. And we explain such types of phenomena in terms of interference between incident and reflected waves. Mathematically, the discrete behavior is enforced by boundary conditions. That means when we mathematically explain the discrete behavior, then we need some boundary condition. Boundary condition about the fixed ends of the string, the clamping of the membrane ring, the size and shape of the enclosure that confines the air columns, etc. So we need some boundary condition to explain mathematically the discreteness of the phenomenon. Similarly, it is tempting to see in the discrete properties of atoms the manifestations of bounded wave motion and to connect the discrete energy levels with standing waves. So these discrete energy levels are somehow related with the standing waves, because you see in the case of vibrating strings also there are some standing waves, and here the quantities such as normal modes are quantized, or there is discreteness about the normal modes of such systems. So definitely there is some relation between normal modes of such system and the discrete behavior. In such a picture, the bounded wave must somehow be related to the confinement of the particle to its orbit. But it is obvious that the concept of an orbit as a trajectory covered with definite speed cannot be maintained. So, in such a picture, as we have told that there is some standing wave, so there is the concept of bounded wave, and this bounded wave somehow be related to the confinement of the particle to its orbit. That is, particles are confined in some orbit. But it is obvious that the concept of an orbit as a trajectory covered with definite speed cannot be maintained. Now, what is a wave? A wave is generally described by its velocity of propagation, wavelength, and amplitude. There is also phase constant of a wave, but as we shall see later, for one particle this is undetermined. So mainly waves are described in terms of wavelength and amplitude and velocity. Since in a standing wave it is the wavelength that assumes discrete values, it is evident that if our analogy is meaningful at all, there must be a correspondence between the energy of an atom and the wavelength of the wave associated with the particle motion. For a free particle, one that is not bound in an atom, the de Broglie relation has already given us a relationship connecting the wavelength with energy. So, it is evident that if our analogy is meaningful, then there must be a correspondence between the energy of an atom and the wavelength of the wave associated with it. The connection between wavelength and the mechanical quantities, momentum or energy, is likely to be much more complicated for an electron bound to a nucleus as in the hydrogen atom, or for a particle moving in any kind of potential. Erwin Schrödinger discovered the wave equation that enables us to evaluate the proper frequencies or eigenfrequencies of general quantum mechanical systems. In this respect, it can be ascribed that the spin of the particles corresponds to the polarization of the waves. However, for many purposes, the dynamical effects of the spin are negligible in first approximation, especially if the particles move with non-relativistic velocities and are not exposed to magnetic fields. So, for this purpose, we will neglect the spin for the time being, much as in a simple theory of wave optical phenomena, where we are concerned with interference and diffraction or with the geometrical optical limits, the transverse nature of light can often be neglected. So, we attempt to build up quantum mechanics with mass, first by use of scalar waves. So, in this chapters, we will neglect the effect of the spin and we will consider only the mass of the particle. Mathematically, the scalar waves are represented by a function psi. Psi is a function of x, y, z and t, that is time. So psi in colorless terminology is called the wave function. Now, as we have introduced the wave function psi, so there is some questions in our mind, that is psi a measurable quantity and what precisely does it describe? That is, can we measure psi? In particular, what feature of the particle aspect of the particle is related to the wave function? So, the main thing is that can we measure psi? That is, can we measure the wave function and what it describes? What is the meaning of the wave function psi? We cannot expect entirely satisfactory answers to these questions before we have become familiar with the properties of these waves and with the way in which psi is used in calculations. But the questions can be placed in sharper focus by re-examining the de Broglie's relation. So what is the de Broglie relation? De Broglie relation is lambda is equal to h by p. Now we can rewrite the equation that is in this way, that is p is equal to h cut k. P is equal to h cut k. Now p I can write in this way, that is equal to h by 2 pi into 2 pi by lambda. So we can write the momentum p, that is equal to h by 2 pi into 2 pi by lambda. The same de Broglie relation, but we have written in somewhat different manner. Now suppose that a beam of particles having momentum p in the x direction is viewed from a frame of reference that moves uniformly with velocity v along the x-axis. So what we are telling, that there is a beam of particles, their momentum is p and they are moving in the x direction, and from which frame we are examining those beam, that is from a frame of reference that also moves uniformly with velocity v along the x-axis. For non-relativistic velocities of the particles and for v very less than c, the usual Galilean transformation tells us that x prime is equal to x minus vt and naturally p prime is equal to p minus mv. So equations 1.6 and 1.7 is from the Galilean transformation. Now, if the particles are in free space, we must assume that the de Broglie relation is valid also in the new frame of reference and that therefore lambda prime is equal to h by p prime is equal to h by p minus mv, because p prime is equal to p minus mv. So if lambda is related to the moving particles, so in the new frame of reference lambda prime will be h by p prime. But according to Galilean transformation, P prime is equal to P minus mv. So lambda prime is equal to P minus mv, h by P minus mv, which is not equal to lambda. We can easily imagine an experimental test of this relation by measuring the spacing of the fringes in a two-slit Young type interference apparatus which in its entirety moves at velocity v parallel to the beam. That is, beam is moving, but the Young's interference apparatus, that is also moving parallel to the beam. So what will be the outcome? So the fringe pattern will broaden. Why it will broaden? You see the relation. Lambda prime is equal to P h by P minus mv. So denominator is less than P. Naturally lambda prime is greater than lambda. The fringe pattern will broaden corresponding to the increased wavelength. Now we all know that classical elastic waves which propagate in the rest frame of measurement with speed capital V are viewed from the moving frame of reference. Their phase phi is equal to kx minus omega t, and I can write kx minus omega t in this way, that is 2 pi x minus vt divided by lambda. So what is phi? Phi is the phase, and phase for what? That is, we have considered that some elastic waves that are moving in space, and that is in the rest frame of measurement, and with what speed? The speed is capital V. And what is phi? Phi is the phase, and phase is the measure of the number of amplitude peaks and valleys within a given distance. If you consider a particular distance for that elastic wave, so for a fixed distance, the number of amplitude peaks and valleys will be the measure of the phi. Now this quantity, that is phase, is a Galilean invariant quantity. If we apply the transformation x prime equal to x minus vt, so in this position, that is phi is equal to 2 pi by lambda x minus vt. Now what we are writing in place of small x, we are writing x prime plus vt according to Galilean transformation. So if we write x prime plus vt, now here, that is in the right hand side, we are taking t as common, and small v minus capital V, that we are writing as capital V prime as per Galilean transformation. So Galilean transformation says that phi should be invariant. So phi is equal to phi prime, that is equal to 2 pi by lambda x prime minus v prime t. Now from the Galilean transformation, we can deduce the Doppler shift equation. Here we have not deduced all the steps for the Doppler shift, but we can show that omega prime is equal to omega into 1 minus small v by capital V. This is the equation of the Doppler shift. Now again, we can rewrite the equation in this fashion, that is in this way. Suppose 1 minus small v by capital V. That means capital V minus small v divided by capital V. So we can write in this way, that is small omega by capital V, that is equal to, in the left side, omega prime by capital V prime, because this V, when it goes to the numerator, so that will become capital V minus small v, again capital V minus small v, that is equal to V prime, capital V prime. So in the left hand side, it will become omega prime by capital V prime, and in the right hand side there will be omega by V. So omega by V is lambda, so lambda prime is equal to lambda. Now the point is that for the classical elastic wave, the lambda is invariant, but whenever we are considering the de Broglie waves, at that time this invariance is not happening. So what is the reason for it? Two explanations come to mind to to resolve this puzzle. But the main thing is that the psi waves, that is quantum mechanical waves, are unlike classical elastic waves whose amplitude is in principle observable and which are therefore unchanged under the Galilean transformation. This thing is very important. That is, for the classical elastic wave, you can measure the amplitude, and this amplitude is unchanged under the Galilean transformation. But for the de Broglie waves, this is not the case. Instead, we must entertain the possibility that under a Galilean transformation, psi changes into a transformed wave function psi prime, and we must ascertain the transformation law for the de Broglie waves. That is, we have to ascertain some special transformation law for the de Broglie waves to remove this conflict. If psi cannot be a directly measurable amplitude, there is no compelling reason for it to be a real valued function. This line is very important, as we cannot measure the amplitude of the psi directly, so there is no reason for it to be a real valued function. In fact, psi may be complex, and by allowing psi to be complex valued for the description of free particles with momentum p, we can resolve the above conflict. So the point is that psi may be complex. There is no reason for psi to be a real valued function. And by applying a local Gauss transformation, there is some special Gauss transformation by which we can change the psi to a new wave function psi prime, so that above conflict is removed. An alternative and in the final analysis equivalent way to avoid the contradiction implied by above equation, that is for the classical elastic wave and for the quantum mechanical wave psi, is to introduce Lorentz transformation rather than the Galilean transformation. So in the Lorentz transformation, we know the equation described here in equation 1.12. We know this relation in the case of Lorentz transformation. If Lorentz invariance of the phase wave psi waves is assumed, then we have to write the transformation for frequency and wave number in this way, that is k prime is equal to gamma into k minus v omega by c square, and omega prime is equal to gamma into omega minus vk. So equation 1.13 gives the transformation relation as per Lorentz transformation for the wave number, and this is for the frequency. Now let us consider low relative velocity, that is we are considering gamma is equal to 1. If we consider gamma is equal to 1, then second of this equation gives the Doppler frequency described in Galilean transformation. So let us look again the second equation. What we are doing, we are putting the gamma is equal to 1. Then omega prime will be omega minus vk, but omega prime is equal to omega minus vk is same, that is same thing which we have discussed in Galilean transformation in equation 1.10. Omega prime here is omega minus omega by capital V into small v. Omega by capital V is k multiplied by v. So this equation will be same if we consider gamma is equal to 1. However, the transformation law for the wave number contains a relativistic term which was tacitly assumed to be negligible in the non-relativistic regime. So now look at this equation. This equation contains the relativistic term, but we have assumed gamma is equal to 1. So this equation will become k prime is equal to k minus v omega by c square. Now what we will do that we will multiply h cut to this equation. So left hand side will be h cut k prime equal to h cut k minus v by c square into h cut omega. Now h cut k prime, that is equal to p prime, h cut k, that is equal to p. So p prime is equal to p minus v by c square into h cut omega. Now let us look at this equation in the case of Galilean transformation. In the case of Galilean transformation, p prime is equal to p minus mv. And now look at this equation, that this equation becomes p prime equal to p minus v by c square into h cut omega. V by c square into h cut omega. So these two equations will be equivalent only when h cut omega is equivalent to mc square. If we put h cut omega is equal to mc square, then this equation will be equivalent to the equation p prime is equal to p minus mv. But this condition, that is h cut omega is equal to mc square, this is reasonable and valid in relativistic quantum mechanics. It implies that for a non-relativistic particle, the phase velocity of the waves is capital V is equal to omega by k is equal to h cut omega by p is equal to mc square by p. And this capital V greatly exceeds the speed of light, and which explains the need for Lorentz transformation under all circumstances. So the point is that if we consider the Lorentz transformation, then the inconsistencies for the invariance of the wavelength can be removed. As we progress through quantum mechanics, we will become accustomed to psi as an important addition to our arsenal of physical concepts in spite of its unusual transformational properties. The wave function psi must in some sense be a measure of the presence of a particle. This line is very important, that is, the wave function psi must in some sense be a measure of the presence of a particle. Thus, we do not expect to find the particle in those regions of space where psi is equal to 0. Conversely, in regions of space where the particle may be found, psi must be different from 0. But the function psi itself cannot be a direct measure of the likelihood of finding the particle at position x, y, z at time t. So psi cannot be a direct measure, but it can measure the likelihood of finding the particle. Why it is so? Because for if it were that, if psi can directly measure the position of the particle, it would have to have a non-negative value everywhere. Yet it is impossible for psi to be non-negative everywhere. Why? Because if destructive interference of the psi waves is to account for the dark interference fringes and for the instability of any but the distinguished Bohr orbits in a hydrogen atom. So for example, if you consider the destructive interference, in that case psi may be negative. So that is why psi cannot be a direct measure of the position, but it can measure the likelihood of finding the particle at some position. In physical optics, interference patterns are produced by the superposition of waves of electric field and magnetic field. But the intensity of the fringes is measured by E square or B square. In analogy to this situation, we assume that the positive quantity mod of psi square measures the probability of finding the particle at position xyz at time t. The absolute value has been taken because it will turn out that psi can have complex values. We will see it later. The full meaning of this interpretation of psi and its internal consistency will be discussed when we will read about Schrodinger equation. So, what we have learned, that is probabilistic interpretation of the quantum wave function for particle with mass. And this probabilistic interpretation of the quantum wave function was first introduced by Max Born. Now, it is known to date, it is consistent with experiment and theory to associate the wave psi with a single particle or atom or other quantum system as a representative of a statistical ensemble. So psi can describe a single particle. Owing to their characteristic properties such as charge and mass, particles can be identified singly in the detection devices of experimental physics. With the aid of these tools, it has been abundantly established that the interference means here there is an experiment. A and B are two slits. So waves are coming from A and B and they are interfering, and here some interference pattern is produced, and at a place PRT, that is these two waves are meeting here and we are getting a particular intensity pattern for the two waves. But the point is that this interference can also happen in case of particles also. In case of waves, interference occurs, and in case of particles also, that is, for example, for the moving beam of electrons, we can also get the interference pattern. Now the point is that the interference fringes shown here are the statistical result of the effect of a very large number of independent particles hitting the screen. This line is important. Suppose we are doing the experiment of interference for the beam of particles. In that case, to get the interference pattern, we have to consider the effect of very large number of independent particles hitting the screen. The interference pattern evolves only after many particles have been deposited on the detection screen. Otherwise, we will not get the interference pattern. So this fact must be noted, that is, we are getting the interference pattern after many particles have been deposited on the detection screen. Note that the appearance of the interference effects does not require that a whole beam of particles go through the slit at one time. In fact, particles can actually be accelerated and observed singly, and the interference pattern can be produced over a length of time. So again, we have to note this fact that we can accelerate the particles singly. It is not necessary, that is, we have to send the whole beam of particles through the slits at one time. Rather, we can accelerate the particles singly, and interference pattern will be produced over a length of time. A particle hitting the screen now here, now there, in seemingly random fashion. When many particles have come through, a regular interference pattern will be seen to have formed. The conclusion is almost inevitable that psi describes the behavior of single particles, but that it has an intrinsic probabilistic meaning. So the point is that psi describes the behavior of single particles, but it has a probabilistic meaning. The quantity psi square would appear to measure the chance of finding the particle at a certain place. So what will be the meaning of psi square? Psi square is the chance of finding the particle at a certain place. An infinite plane wave we have discussed earlier, that is an infinite plane wave as representative of a free particle with definite momentum but completely indefinite position. So we can describe the free particle in terms of a plane wave, but a plane wave has a definite momentum. That is, it can describe the wavelength clearly, but it has completely indefinite position. At least if psi is so interpreted, the observations can be correlated effortlessly with the mathematical formalism. These considerations motivate the more descriptive name probability amplitude for the wave function psi, because as we have already discussed that psi has a probabilistic meaning. Psi can describe the behavior of single particles, but psi has a probabilistic meaning, and psi square is a measure of the chance of finding the particle at some particular place. So we can say, so what is psi? So psi is the probability amplitude. The more descriptive name can be given, that is, it is probability amplitude. But as a word of caution, we note that the term amplitude as used in quantum mechanics generally refers to that space-time dependent wave function psi, because psi is space-time dependent and not merely to its extreme values. Extreme values means, for example, in classical physics, amplitude amplitude can be measured specifically. But here the meaning of the amplitude is that psi is space-time dependent. The indeterminism that the probabilistic view ascribes to nature and that still endangers discomfort in some quarters can be illustrated by the idealized experiment that has been shown in this figure. Single particles are subject to wave interference effects, and some are found deposited on the screen at locations that they could not reach if they moved along classical paths through either slit. So what is the meaning of this sentence? That is, if we send single particles, through the slit, but still we can have the interference effect. And as we are observing interference effect, for example, this is the interference pattern. So for example, this is the peak of the intensity. It is a peak. This is the strongest peak. So this meaning of the peaks is that there is a chance for finding the particle. But if you send particles singly, then according to classical physics, it will hit at some particular place. But mechanically, as we are observing a interference pattern, so there is a chance of finding the particle in these maximum positions. But classically, it is not so. The appearance of the interference fringes depends on the passage of the wave through both slits at once, just as a light wave goes through both slits in the analogous optical Young interference experiment. That means, although we are sending particles singly, that means those particles will pass through a particular slit. But as we are observing the interference phenomena, so the wave corresponding the particles pass through both of the slits, otherwise there will be no interference. So actually this experiment suggests that particles have some wave-like properties. Although we are sending single particles, but classically it is apparent that particles will pass through some particular slit, and not simultaneously through the both slits, because we are sending single particles. But as we are observing interference pattern, that means there is some wave-like properties, and these waves are passing through the two slits, and ultimately we are observing an interference pattern. If we try to avoid this consequence by determining experimentally with some subtle monitoring device through which slit the particle has passed, we change the wave drastically and destroy the interference pattern. Suppose if we wish to see that through which slits the particles are passing, that is, we are introducing some monitoring device to see that through which slit the particle has passed. In that case, the interference pattern will be destroyed. That is, when there will be particle nature, at that time we will not get the interference pattern, but when we will consider the wave nature of the particle, then there will be the interference pattern. In the language of the principle of complementarity, the conditions under which the interference pattern is produced forbid a determination of the slit through which the particle passes. This impressionistic qualitative description will be put on a firmer footing in later discussion. We will discuss in our later lectures. An alternative view of the probability interpretation maintains that the wave psi describes only the statistical behavior of a collection or ensemble of particles. Actually, we deal with the ensemble in statistical mechanics, and this is an alternative description of the probability interpretation. The alternative description is that the wave psi describes only the statistical behavior of a collection or ensemble of particles, allowing, at least in principle, for a more detailed and deterministic account of the motion of the single systems that make up the ensemble that then is sanctioned by quantum mechanics. So this is another interpretation of the probability interpretation. But the main thing is that psi fully describes the statistical behavior of single systems. So we can summarize in this manner, that is, in quantum mechanics, indetermination of which we have just given an example is a property inherent in nature. This is the main thing, that is, indetermination of which we have just given an example is a property inherent in nature. And the most notorious imperfection of quantum mechanics being the abandonment of strict classical determinism. So in classical physics, there is a strict determinism. For example, you can measure position, you can measure the momentum, and all this can be measured simultaneously. That means there is a strict determinism. But in quantum mechanics, there is no strict determinism. For example, according to Bohr's complementarity principle, you cannot measure the position and as well as the momentum of the particle. So there is some indeterminism in quantum mechanics. But quantum physics can be said to provide a more comprehensive and complete account of the world than that aspired to by classical physics. So this is the importance of the quantum physics over the classical physics. So this is the end of the lecture, and I request you to go through the textbook of Mark Pager for more clear understanding about this topic. Thank you all.